Right, Master of Science students, welcome back. Let's continue to on this session on the Hammett plot. I must say that Hammett plot, because of its relationship to mechanism, is quite a wide topic, and I think you can see that we've had more or less like this could be the seventh, eighth, or close to 10th video on these topics. But I think at the end of it, you'll see how uh, the Hammett plots are really going to help you understand about mechanism. So, so we're looking at the uh, the plots. I mean the gradient in the when you're going to be plotting the log base 10 of the rate constant of the substituent which is attached at the x position. In this case, it's at the meta or the para position. In this case, you've got groups like maybe methyl group, methoxy group, amino group, chloride, what cyanide, and nitro group, something like that one, yeah. So they are attached at either meta or the para position. We say that you are omitting the ortho position because uh, at that position they are going to be next to the to the reaction center, and therefore there will be interference and they're not going to fit on the curve. Yeah. So uh, so there will be the log base 10 of the rate constant, and the H is the unsubstituted benzene. In this case, one in which there is no substitute. And then this is the sigma. And the sigma was saying is from the pKa of the unsubstituted benzene, and you subtract from it the pKa of the substituted group. Yeah, I think we derived on that one on how to get the raw value. So in this, not the sigma value. So in this case, which means that if you are given those figures, you can be able to determine the plot here. Now, we're saying that the raw value has a lot to talk about. The flow of the electrons either towards the reaction center or away from it uh, in the rate determining step. So, so you just need to know what do you call it? If okay, they are this opposite. When the row is positive, the electrons there is a building up of the negative, which is the negative value on the reaction center in the transition state. And if the row is negative, then there's a building up of positive charge in the transition state of the rate determinant step. So you just need to know that one, yeah. Yeah, negative row building up of positive charge. Positive row building up of the negative charge in the transition state of the rate determinant state. You'll remember that, yeah? Okay, it's just, excuse me, let me remove some of these things which are making noise. Okay, good. So, uh, so in this case, this raw value, it means this is the plot which is positive. It means that the electrons are flowing into the aromatic ring in the rate determining step, RDS, yeah? And if the row is negative, it means that the electrons are flowing away from the aromatic ring in the rate determining step. I don't know whether you can be able to see well or you'll be able to zoom. In this case, uh, uh, in the plot, it means that the row can be negative. I mean, there's the negative on the plot, and in the negative, it means that the electron donating groups are the ones which give a negative row. So that in this case, electron EDG is electron donating group, like the methyl, methoxy, OME is methoxy, and something like amino group. Yeah, and then electron withdrawing group like the chloride, the what? That is the ester group, CO2R. R is an alkyl group. These are CN, that's a cyanide, and the strongest electron withdrawing group is the nitro group. Yeah, are you okay with that? So the positive, the groups with the positive sigma values like the chloride, ester group, cyanide, and the nitro group. And the ones with the negative value are like methoxy, methyl, and amino group, something like that. Yeah, yeah. So this is something just to remember, and I think I'll be able to prepare this item, but very rarely will you get. Now this is giving you an overview of the typical plot values, which is the raw value, and what it means. Very rarely will you get uh, if the plot is negative, the typical value is up to -4, and the typical value if it is positive is up to +4. Very rarely will you get -5 to -6, and very rarely will you get +5 to +6. So that you are going to see dash here, because what it implies that in this case, if it is -5 or -6, it means if the plot is -5 or -6, it means that you are actually having a positive charge on the benzene ring itself. Yeah, so it means that rather than the reaction center attached to the benzene ring is now undergoing a reaction in which there is a positive charge on the ring itself. Yeah, and that will mean that if you're going to have something like a like a what, like a benzoic acid, and then you've got a positive charge, it means that there is a severe destabilization, because in this case you've got a positive charge directly on the benzene, and therefore those are extreme cases. And then also +5 and +6, it means that there is positive and a large negative charge on the benzene. It means that these are not cases whereby you're simply going to have a, a group attached to the benzene ring. Here you have the benzene ring itself, the aromatic ring, undergoing a reaction itself. So these are extreme cases, yeah? But the typical values are between -4 and +4. So it means that in this case, from -4 to -2, it means that there is a negative positive value on the ring. This moderate negative value on the ring, near the ring, yeah? And then there are these values uh, uh, that if the raw value is is between -1, it can be -1 or +1. Let me say that when it means that the aromatic ring is far away. So it means, what does it mean? It means that assuming you've got an aromatic ring, and then you've got your X here. Maybe I may have a case whereby the I mean the maybe if this is your reaction center, then there are so many alkyl groups here. So this group is not it's not affected much by by either the electron donation or the electron withdrawing group, yeah, because it's really far away. So the raw value will be close to 0, because the aromatic ring is too far away from the reaction center. What it means that there are many alkyl groups between the ring and the reaction center. If the value is between -1 and +1. Now, the other thing is that there could be no uh, electron change, yeah. Uh, so there is no uh, building up of electron charge or withdrawal of electron charge on the reaction center. And then the most tricky part of it, which you're going to be seeing, is that you may be having a reaction whereby uh, that there is, I think this one I'm going to be seeing later, that there is a rate determining step in which in the same reaction there is a change in the reaction stage, whereby there is probably a plot is coming down, and then after some time the plot is coming up. You're going to see those type of curve. So if there are going to be two curves within the same area and they're going to be canceling one another, then you're going to get a raw value being 0. But that does not mean that the aromatic ring is far away or there is no electron change, but it means that you've got two raw values which are cancelling one another for the same x value. Yeah. So I think this that's what I may need to talk about. The raw value, which is the plot. It has a lot to talk about the mechanism. As we come to an end of this section, I need to tell you, I need to refer you to the book on the Hammett plot or Hammett equation. Uh, it's in the Google Docs folder. So you just look at it and you'll be able to see uh, that book is totally dedicated to the Hammett plot, but you may go to advanced stage, but that will not be examined. The things which I'm just talking gently is the fact there are things which are likely to be uh, yeah, to be examined. Yeah, are you okay? So so what you're going to see is that as you're going to be plotting the sigma values, you're going to see sometimes some uh, some figures can be here, they can be down here, they can be here. Then others are close to the center, then others are out here. Yeah. So rather than dismiss these plots as to the the values which are not uh, fitting along the line, what scientists did was to find out the reason why they are not fitting on the line, and what it was found is that if the X group is especially attached to the para position, then there is conjugation directly between that group, the way it is donating electrons or it is withdrawing electrons to the reaction center. So that can cause the sigma value to be much stronger or much less than would have otherwise be. So they developed modified sigma values. So that means that if you're going to apply that correction, then the value, like for example, if you're going to have something like the nitro group or amino group and the rest, if they're going to have those conjugation effect, if you're going to use those modified sigma values, then the value is going to fit directly on the plot. And I think later I'll give you a document showing the various corrected or the modified sigma values uh, that are not the ones which are determined experimentally, but the ones which have got the correction to be able to make them fit on the straight line. So for the ones which are going to be donating electrons and they're going to be strongly electron donating group, you're going to have what sigma para, and then there will be a plus. That will distinguish them from the sigma pia. It means that these are sigma values at the para position. So if there will be the plus, it means that these are the modified values. Yeah, the corrected values. So, and once again, I'll give you a document on that. So the sigma plus or the sigma values for the para which are going to be donating are going to be what? The values are going to be negative, yeah, for the electron donating group. How about the ones for the electron withdrawing group? In this case, you're going to be having sigma p negative. In this case, you have a group which is withdrawing electrons. So those sigma values are going to be positive, are going to have positive values for the electron withdrawing group. Yeah, is that clear on that? So these ones are going to be positively charged. I mean, are going to have positive values. These ones are going to have negative values. Yeah, for the strong electron donating group, the ones which are electron donating are going to be negative values. For the electron withdrawing group are going to be positive. Yeah. Okay. So the modified sigma values will enable the sigma values to fit on the straight line for the conjugation effects. Yeah. Are you okay? Yeah. So I think that's the much I'll talk about these sigma values, and uh, the next thing I'll talk about will be uh, the nonlinear Hammett plots. Nonlinear Hammett plot. The ones that you've been seeing have been straight lines, but you're going to see there are some plots which are not linear. They may they appear like a U. Yeah, yeah. We are going to see what information you can get from those nonlinear Hammett plots. Yeah. I hope you're enjoying this session. Okay. All right. So we'll stop there.